All right, so for my last story, I want to go back in time and talk about something that you probably saw in the news if you pay attention to astronomy and space science news. So Phil Plait wrote about it last year about this star called KIC 8462852, but that's a mouthful, so people call it Tabby's star, named after Tabitha. I can't pronounce her name, but I'll see it. The astronomer who first wrote the paper about this. But this made a big splash last October, or October in 2015, because this particular star was so strange by its behavior that people didn't know what to make of it, including all the astronomers studying it. And so here is a headline from Popular Science: could a black hole be blocking the light from that alien megastructure star? Well, the answer is no, but and we'll discuss why. But it definitely got people excited, and even then, you can see, this headline came out just last November, and so let's talk about what is so unusual about this star. And I purposely didn't talk about this in the past year, just because there was a lot of speculation, but it didn't seem like people had any firm ideas about what was happening. But now I think we still don't quite really know what exactly is going on, but I think the theories that people are proposing seem a lot more reasonable and not so crazy and out there. So it seems like a good time to bring this up again. But this particular star was found by the Kepler Space Telescope, and this is a telescope that is designed and is still in operation, but it's designed to find planets around other stars, what we call exoplanets or extrasolar planets. And the way that it does that is it looks for a slight dimming of the light from the star when the planet orbiting passes right in front of the disk. Obviously this is a cartoon. The stars don't look really this big, but this gives you an idea of exactly how it works. And what Kepler did, at least in the first phase of its mission, was to stare at a spot in the constellation of Cygnus. So here is Cygnus, the swan. This is a constellation that you can see high in the summer sky, and you can see the wings of the swan, the butt of the swan, the neck of the swan. It's basically flying down the Milky Way, but the satellite stares at that exact same spot the entire time, basically over a course of 4 years. And it keeps taking observations over that time, looking for those events when, if you have a planet pass in front of the star, you'll actually be able to record the dip in the starlight. And so here is the set of cameras that are on board Kepler. So you can see that the cameras match the footprint of the field of view. This is a pretty large patch of sky, and it was observing about 150,000 stars in total. And you really have to look at a lot of stars in order to record that chance. The star has to be oriented right, so you can't have a face-on orbit. The orbit has to pass directly between us and the star, or the planet has to pass directly between us and the star, and you have to watch it long enough for the planet to pass. And so here is some data from the Kepler satellite for one particular object, and you can. This is the brightness of the star, and then when the planet passes by, it has a slight dip. So that dip is due to the transit of that planet, and then when the planet passes off the disk, the starlight goes back to being 100%. And that dip, you can see, is less than 1%. So it's 99.4 or 0.3 here. So that's about 0.7%, 0.6% in this case. For Jupiter transiting the sun, Jupiter is a large planet. It's the largest in our solar system. And even Jupiter would only subtract about 1% of the sun's light if an alien astronomer was looking at our sun, looking for transits. And then based on the timing of these transits, you can determine information about the planet's orbit. But what was really weird, and then here are some other examples of transits of different exoplanets. And so in this case, for a really small planet, you can see that the amount of change in the drop of the light is very, very small. As you get to larger planets, you get a bigger dip, and then the width of these dips will depend on how quickly the planet is orbiting. And so you're seeing orbits that are very fast, and that's because these planets are orbiting very close to their parent stars. So in this case, Tabby's star is here in the constellation of Cygnus. And this particular paper, so there's your last name, Boyajian. I'm probably butchering the pronunciation, but this paper came out last year, early last year, in 2016, and what was really exciting about this paper was that this actually involved the work of citizen scientists. So there are actually projects online. You can go onto the internet, and this particular group was the Planet Hunters group. It turns out that there's so much data coming back that came back from the Kepler Space Telescope that they do use computers to try and tease out those transit curves. So the curves that we saw here, these are pretty regular, so you can write a computer program to find these very regular drops in brightness. But they wanted to have human eyes looking at these as well, because there could be things that the human eye can pick out that the computer can't, or that you haven't been able to program yet into the computer. And so there are a number of people who actually found the weird signatures in this particular star. And so in this paper, all these people who have the 2 superscript in their names, they were actually amateur astronomers, part of this team that actually found the weird signature. Now, this is such a weird result, and the rest of the astronomers didn't really know what to make of it, that they put something in the title to let you know that they were really confused about what they were seeing. Can you spot what that was in the title? Here's the hint. WTF. All right, so this is what is really weird about the star. This is 4 years worth of data. So for the most part, and this has been scaled so that the brightness of the star is at 100%. And they have a bunch of these dips. So instead of having regular dips, which you would expect from a planet that's in a regular orbit around the star, they have dips that are not regular at all. They seem to come almost randomly. And some of them, and they're also not the same size. So here's a dip that's maybe half of 1%. Here's a dip that's much larger, and then and these are dips that are much larger still. Here are close-ups of some of these dips. So these dips are not necessarily symmetric. So they have, one side is curved differently than the other side. And then when you start looking at these other dips, these later dips, you can tell that it looks like there's multiple dips that are occurring. So it's not, one object, if this is caused by transits, but it could be multiple things orbiting. But it seems really confusing because things in orbit you would expect to have some sort of regular pattern, but there's really no rhyme or reason to these dips. And some of the dips actually go down to almost 20%. So there's really nothing that we know of. This is part of the speculation. It becomes really difficult to imagine what sort of thing can cause the starlight to dip by that amount. And the other confusing aspect of this is that this particular type of star, an F star, has been very well studied, and we know how they work. We can simulate their evolution, and we don't expect even the star to have anything intrinsically weird with them that would cause their brightness to change like this. So after this paper came out, another astronomer, Brian Schaefer, went and he found archival photographic plates of the night sky, and he found that there were plates that observed this particular part of the sky. And so he was able to go back basically 100 years, from about 1890 to 1990, and show that the star actually seems to have decreased in brightness over that 100 years. So the Kepler results are only 4 years long. Here we're seeing evidence that there's 100 years worth of dimming. And this amount of dimming occurred, or dimmed the star by about 14%. And the dots here are control stars. So those are other stars that he found in those photographic plates that he also went and reduced the data just to show that this isn't some weird artifact of how the plates were analyzed, or the photographic plates were degrading over time. Other stars showed consistent brightness. It's only this particular star that showed dimming. And then another set of astronomers came out with a paper last year where they went and analyzed all the Kepler data really, really carefully. And what they were able to show is that in addition to those weird sharp drops, you can sort of see here and here, they were able to analyze the absolute change in the brightness of the star instead of the relative change. And so what they showed was that for more than the first 2 years of the mission, the brightness was dropping about 0.3% per year. And then towards the latter, the end of the mission, it was plummeting by about 2.5% per year before leveling off. And the first phase of the mission ended here, and Kepler wasn't able to observe that patch of sky any longer, so we don't know what's happened since then. So this, again, is very, very puzzling. Now, as far as what could be causing this, there's been a lot of speculation. One is, perhaps this is a very young star, a protostar, and we know that very young stars have a lot of variability, but people have observed this very carefully. There's no sign that it's a young system. Another possibility is that perhaps there are collisions with planets in the system, and that's causing lots of debris. And so the debris ends up masking the starlight as it orbits around the star. But you can see, you should be able to detect the debris in the glow of infrared, and we haven't detected this, so this isn't a very good idea either. Another idea, that was actually proposed by Briagen and her team, was that perhaps this is a swarm of comets. This particular star actually has it might be part of a binary. The second star is much further away, and it's thought that the second star could, in its orbit around the main star, cause comets to get ejected and to get into weird orbits. And these clouds of comets, as they're orbiting the main star, so here's that second redder, smaller star, they could, again, block the starlight. So this is possible, but it's also not satisfactory because, again, you need lots and lots of comets in order orbit for this to happen. And even though this might momentarily block the starlight, this doesn't explain the steady drops or the dimming over many years, over 100 years. This doesn't really do it. And then if you do an internet search for Tabby star, you start seeing pictures like this and this. So the other idea that kind of came out that was kind of crazy is the idea that this could be a Dyson sphere, that there could be an alien civilization living in orbit around the star, and they decided to basically build a structure that would collect every single bit of starlight that they can, because they needed all of that energy. And so since they're still in the process of building this, you'll see weird dimming because this is very irregular. But again, this is problematic because even though it's collecting all this light, it should still radiate in the infrared. And again, we don't see any weird infrared signatures as yet. So that gets us to the paper that just came out. And what this paper does is it actually does seem like it does a good job of explaining both the what is called a secular, meaning the long-term dimming, the one that happens over the course of many years, even 100 years, versus the transient dimming, the sharp spikes that we see in the light curves. And what they propose is that if you have that second star that's disrupting planets in the orbit around the main star, you could actually cause those planets or moons to plummet into the star, to spiral in. And when they plummet in, they add energy to the star. And so what we're seeing is is basically the tail end of the star returning to its normal brightness after it's gotten an infusion of energy that causes it to brighten. And so we missed the brightening due to either a Jupiter or a brown dwarf or even an Earth or Io-sized object, a moon-sized object falling in, but we're basically seeing the tail end. And this bottom plot basically shows the amount of change, the long-term change seen by those two different authors that we saw plots from. And you can see that the amount of energy or the change in luminosity over time as the star decreases in brightness, you can actually explain it by having these objects fall in. And so this particular model, again, explains basically the long-term, or the secular dimming, as well as the short-term dips, because if the solar system is disrupted enough for planets to fall in, you would expect lots of debris as well. So the short-term dips could be due to that debris. And then for the model to work, and these are the things that are required, you actually need lots of planetary bodies, so you can't just have one or a couple. You need a lot for us to be lucky enough to see it during the time that we've observed it. And it's actually not quite clear whether the second star is actually a binary. It could just be in the same point in space. So further observations need to be done in order to determine that. So we need further observations to see whether it's actually a binary system, but we also want to look during a deep transit to actually look for evidence of the planet or the material that's in orbit. And then what would be really cool is if another planet actually falls in and causes the star to brighten, in which case that would be really good evidence that this indeed is happening.